Okay, we have defined work, kinetic energy, gravitational potential energy. In this video, we're going to define another type of potential energy, which is associated with force in a spring. So, elastic systems, if you are familiar with elastic systems like, for example, a spring. Spring is an elastic system. When a spring is stretched or compressed, you can feel there's always a force inside the spring to try to bring it back to its original length. Right? If you stretch a spring, you'll feel that it wants to pull the spring back to its original length. And then if you compress a spring, you feel the spring has a force, wants to push you back again to its original position. So we call this force a restoring force. It always wants to go back to its original length. And then the force inside a spring actually has again, very nice equation to calculate that force. We call it Hooke's law, which was discovered by Hooke. This K is called the spring constant or force constant of a spring, and the unit is newtons per meter. And that's because when you multiply K with the delta x, the displacement, you want to get newtons. So the K is in the newtons per meters. Again, this is a vector equation. Whenever you see a vector equation, you should be careful. What does this negative sign mean? This negative sign just means the force, restoring force, is always going to be opposite to the displacement. Does that make sense? Take a look at this image on this slide 14. If you if you stretch the spring, right? If this is the original length of the spring, if you stretch it to the right, so the displacement is to the right, right? You stretch it from this point to that one, that's the displacement. What is the direction of the force? The force is going to be in the opposite direction. So the force and the displacement, they're always in the opposite direction. That's why they're the sign, right? If you compress the spring, then this is the displacement. You compress the spring to the left, and the force in the spring is going to be to the right. It wants to go back to its original length. So the force in a spring is always opposite to the displacement. So that's why we have a negative sign there to represent the direction of the force. But when I use a vector equation, I'm very careful. I would always do that in two steps. So I would always just make sure that I use all these absolute values, these magnitudes. If I want to do algebra, if I want to find any of these three guys, and then I take a look at the direction of the displacement to find the direction of the force, or I take a look at the direction of the force, I can find the direction of the displacement, right? Because I know if I understand that they're always opposite to each other, which is I hope it's intuitive to everyone. So I don't really need to use this equation to figure out a direction, okay? Because physicists always want to write a nice equation which has all the information in it. When I see this equation, I know everything. But what this equation actually tells you is this. When you calculate the magnitude, you make everything positive, you manipulate this equation to get the magnitude of everything. And the direction, force, is always opposite to the direction of the displacement. But when I use this equation, I just use that in two steps. Now, there's a way so this K is a property of a spring. So in order to find this K, again, you need to do experiments to find this K. A very simple experiment is this experiment on slide 15. So if you want to find the K, you would do this, right? I would rearrange this equation. I would stretch this spring to some displacement and just divide the force by the displacement, I can get the K. But finding the force in the spring is a little bit hard. But if you make use of gravity, like in this experiment, then it's going to be very easy for you to find the force in the spring. So let's take a look at this experiment on slide 15. A common technique to measure the spring constant is to attach a mass to the lower end of a spring hung vertically. So you're going to attach the upper end of this spring to some place. And then you're going to place a mass to the lower end. Then, of course, the spring is going to be stretched because the object has gravity. Gravity is down, so this gravity is going to stretch this. It's going to pull this spring down. So the spring is going to be pulled down like this, right? So this is the original length of the spring, and then if you attach a object to the lower end. So now you see that, now you can measure the displacement of the spring very easily, right? You just measure the original length, the final length, and then this difference is going to be the displacement. So this displacement is always going to be the displacement. So the symbol is theta x, but this doesn't have to be always in x direction, right? It's always a displacement from the original length, the equilibrium point of the spring, to the final point. All right. So you can definitely measure this displacement very easily. In this problem, it says that, okay, it's just going to be stretched a distance 3 centimeters. Okay, you already know the displacement. This is a problem. But this is something you can measure very easily in an experiment. And then if I want to find the K, I would need the force in the spring. The force in the spring is a little bit hard to measure, but if I can make use of Newton's laws in this case, because gravity of this object is down, right? And then the spring force is also on it. The spring force wants to bring the spring back to its original length. So the spring has a force in the opposite direction, right? That's going to be the spring force. And then if this guy, when you do this experiment, you attach a mass, an object to the lower end, so it's going to be stretched, so it's going to oscillate a little bit, but you wait a little bit until it settles down here, so it stays here. That means these two forces, they must be equal. So instead of measuring this force, all you need to do is just measure the mass of this object, and because these two forces are equal, according to Newton's laws, then this number is going to be the number I use for the spring force. And this number is easy to calculate, right? You measure the mass of this object using a scale, and then multiply it by 9.8. So that's how we measure the K of a spring in the real experiment, and we can even do that in the classroom. Okay, so in this case, if we know the mass of the object is 0.5 kilograms, I want you to do the algebra and find the spring constant for me. Okay, so what is the spring constant you find? So if I rearrange this equation, this is what I get, right? Everything positive because I'm working with these magnitudes. And in this case, the spring force will be equal to the gravity of this object. And then plug all the numbers in. I should get 163 newtons per meter, right? Because the problem says this is 3 centimeters and the mass is 0.5 kilograms. All right, so that's an experiment we can do in a classroom to measure the K of a spring. Now again, I want you to take a look at this spring. So initially, if I attach the mass, right, initially I would attach the mass at this point, then it's going to drop. When it drops, take a look at the gravitational potential energy. Does the gravitational potential energy of this object change when it drops to this height? Of course it does, because the height gets lower. So if I compare the gravitational potential energy goes down in this experiment of this object. Where does that energy go, right? You have to make a complete consistent theory. This energy can't just disappear, right? Where did this energy go? That energy goes to the energy inside the spring, because now the spring has been stretched. So we have to define another type of energy in order to, again, make a complete and consistent theory. So in this case, the gravitational potential didn't just disappear. It just becomes another type of energy stored in this spring. We call it elastic potential energy. And the elastic potential energy has a definition which can be derived, but we're not going to derive it here. We're just going to go ahead and use this definition. So it's 1/2 K delta x squared. So this delta x is the displacement of the spring from the equilibrium point, from the unstretched point. So this unit, again, it's going to be Newton times meter, and that's going to be in joules. So all energies and work, they have the same unit. That's why they're connected. And then this force in the spring and the force of gravity, they are conservative forces. So there's a fundamental theory in physics about conservative forces. So take a look at these facts in slide 17. We're not going to really go into detail about conservative forces, but these are the conclusions, okay? If there's a conservative force, the work done by a conservative force between any 2 points is independent of the path taken. So any 2 points, you draw a path, totally arbitrary. The work done by this conservative force, it's always the same. So, and then if you make a loop, you have this conservative force doing work in a closed loop, and then it's going to back to it's a closed path. It's going to back to its own the starting point. Then the work done is always going to be 0. So if there is a conservative force, you can always define a potential energy associated with this conservative force, and the theory is on this slide. So that's a fundamental theory in physics. We don't need to really worry about that theory in this class, because this is an intro-level class, so I'm not going to ask you to really study that theory. We just need to know this fact. There are some conservative forces in nature. Gravity is a conservative force. That's why we can define gravitational potential energy. Spring force is also a conservative force. So that's why we define elastic potential energy associated with this force in a spring. Electric force is another conservative force. You're going to study in physics 2 if you're going to take physics 2. So we're going to define electric potential energy in physics 2. All right? So in this class, we're just going to be dealing with work and these 3 types of energy. So sometimes you're going to see this term mechanical energy. Mechanical energy is just a name for the sum of kinetic energy and all the potential energies of the system. It's just a name we define. We just call, sometimes we want to find out the total energy, the total kinetic plus potential energies in the system. Why don't we give it a name? We call it mechanical energy. All right, that's just another definition, just sum of kinetic energy and potential energies. So we have already seen the connection between work and energy. Work, it's a way to transfer energy, right? You do work to a force doing work to a system, to an object. It can change the energy of the object, right? It can increase the energy or decrease the energy. And energy, if something has energy, it has the capacity to do work, right? If you want to go to the gym and do work, of course you need to eat. You need to have a lot of energy so you can do that. You can work out. So that's a connection between them, right? Doing work can always change the energy of something, and then having more energy can always do more work. So there are other ways to transfer energy, mechanical waves, heat, matter transfer, EM in radiation. There are a lot of ways to transfer energy. There are also different forms of energy other than these 3. Like thermal energy, chemical energy, electrical energy. But in this class, we're just going to discuss one method of transferring energy, work, and then 3 different forms of energy. So there's a very fundamental law in physics in this universe. It's called conservation of energy. That's a law we discovered in nature. And this is a very intuitive law, I believe. It just states that energy can neither be created or destroyed. Very intuitive, right? You can't destroy energy, you can't create energy. You can only transform it from one form to another, or transfer it from one system to another system. You just can't get anything from nothing. Very intuitive, I believe it's very intuitive. Right? So if you want to put it in an equation form, what I usually do is this. Okay, I would write it this way. So if there's a closed system, I can calculate the change in the energy of the system. It's always going to be equal to the energy transferred into or out of this system. Very intuitive, right? So this T, I use this T to represent any energy transferred into or out of the system. And I can use signs like positive and negative to distinguish into and out of. All right. So of course, if this T is 0, if there's no energy transfer in this between the system and the environment, so the total energy of the system will remain constant. So that's conservation of energy. In this class, as I said, we only discuss these 3 forms of energy in a system. We only discuss one method of transferring energy, which is the work. So this equation is going to become this in our class. So that's the equation we will use if we apply conservation of energy in the problem. We're going to, again, do some practicing with conservation of energy, because this is another law we learned. So if you read different books, again, different books have different notations. They have different ways to present conservation of energy. So that's the notation I usually use. The change in the energy of the system, which is going to be 3 different forms of energy in this class. It's going to be equal to the work from the outside. So that's why we have this subscript ext here. It means that you calculate work done from any external force from the outside. You don't calculate work done from the force between any objects in a system, because a system can have many, many objects, right? So of course, if there's no work done from the outside on the system, then the total energy of the system is going to be 0. Then how do we apply this law in the real problem? You're just going to write out every term, and then you're going to manipulate this equation. You can find things you need. The left-hand side is always easy to set up. Why? Because everything has a very good definition. Kinetic energy is always 1/2 mv squared. And then when I calculate this, don't forget this change. If I want to calculate change in kinetic energy, that's always going to be final minus initial. And then how do I calculate the final kinetic energy? I'm just going to use this definition. The only thing I need to change is going to be the final velocity and the initial velocity. The mass of an object is not going to change. And then you do the same thing for the gravitational potential energy, right? So you do final gravitational potential minus the initial potential energy, gravitational potential energy. And again, the only thing that's going to change for the same object is going to be the height. So you just use final height, initial height. And then the elastic potential energy, if the same spring, K doesn't change, so the displacement will change. So you're just going to find the final displacement and initial displacement. And you're going to have to write these 2 terms. So each of them is going to give you 2 terms. Right? And then sometimes you may have many objects in your system. So you're going to get data K for every object. You're going to get data UG for every object, data US for every object. So you may have a lot of terms. You may end up with a lot of terms on the left. But you always know how to set up the left-hand side, right? Because you just do final minus initial for each term for each object. Okay? So that's how you set up the left-hand side. The right-hand side, the work, then you're going to calculate the work done by each external force. And how do you calculate work? Work also has a definition. Use this definition, and then you're going to repeat this definition for every single external force. So you should be careful. Any force inside this system, we're going to see some examples. If there's some forces between the objects in your system, you don't need to calculate the work done. So which is nice, right? You only need to worry about the force from the outside. You don't need to worry about the complicated forces inside the system. And because there are 2 forces very special in conservation of energy, if we defined gravitational potential energy, we already included gravity in our system. If we defined elastic potential energy, we have already included the spring force in our system. So these 2 forces, if you use their potential energies on the left-hand side, you don't calculate their work done on the right-hand side. They are already in our system. They are already internal in this equation. The effect of the gravitational force and the spring force, it's already in these 2 terms. So you don't need to calculate that, the work done by these 2 forces on the right-hand side. Otherwise, it's going to be a double count. So which is very nice. All right, so you only need to calculate force, the work done by forces other than gravity and the spring force, and also the forces inside the system. So the right hand side, even though there may be many forces in this problem, the work you calculate on the right hand side actually can be like very few. All right, so that's how we apply this law in a real problem. So now we're going to practice this law in some real problems. So let's take a look at the next PowerPoint 11. So let's first use a problem we have seen before to practice law. We have seen this question before, right? When we were practicing kinematic equations. Because this is a free fall, right? The student throws a stone from the top of building with the initial speed, and then after the stone leaves the person's hand, it's totally under gravity, so it's free fall with the initial velocity. So it's going to go up, slow down, and reach the top, and then turn around and drop, right? So we want to practice this part again. We want to find the velocity of the stone when it is 32 meters above the ground using conservation of energy. I know I can do that using kinematic equations, but now I want to practice this new theory. All right, so let's do that. So this is going to be the motion of this stone, right? So it starts from a point 50 meters from the ground. I want to find the speed of this stone when it's 32 meters above the ground. So it's still falling. Now, how do I find that? We're going to use conservation of energy. If I use conservation of energy, that's the law I'm going to write down. Always delta K plus delta UG plus delta US. All right? So, and then, as I said, the left-hand side is always easy to set up. You just use the definition. You may end up with a lot of terms, but that's fine, because you always just use the definition. Delta K, there's only one object moving, the stone. So I'm just going to write down final minus initial kinetic energy using the definition. Now, gravitational potential energy, final minus initial, that's the change. Right? And elastic potential energy is only associated with the spring. In this case, there's no spring, so I get a 0 here. All right. Now we're going to take a look at the right-hand side. External work. So you're going to find the work done from the forces outside the system. So let's see how many forces on this stone when it's in the air. Well, only gravity is on it. Because it's in free fall, only gravity is on it. So only gravity is on it, and as I said, we already defined gravitational potential energy on the left-hand side, so gravity is already, it's always in our system when I apply conservation of energy in this form. So the force from the outside in this problem is 0. There's no force from the outside. Gravity in our system, always. So that's going to be 0 on the right-hand side. Okay, very nice. So now let's see. I want to find the velocity at this point, so let's call this final. And I know the velocity at this point, so I'm going to call this initial. So that's going to be initial and final. So I don't care how complicated this process is. I don't need to worry about that. I just set up final and initial, find the work in this, between these 2 points, and rearrange this equation. So in this case, we do know the initial velocity, right, which is 18 meters per second. So that's going to be the VI I plug in. So I will have this term. And then first of all, you see that the mass is going to cancel out in this equation because I don't need the mass. Every term has mass. So I can divide both sides by little m, so I will just get this. If I divide both sides by little m. So you don't need the little m in this equation. Then, initial velocity, that number, do I know these 2 heights? Yes. It starts from here. If I call initial height is this initial point and this point, that's going to be the initial height I plug in. If I call this point final height, final point, this is the final height I plug in. So I know all the numbers here. I just need to rearrange this equation, find this VF. Okay, so now you can pause the video, rearrange this equation, find the speed of this stone when it reaches 32 meters above the ground. All right, so let's see, what is the number you got? So you just rearrange this equation, right? You will get 1/2 VI squared. You move it to the right, minus GH final plus GH initial divided by 1/2, and then square root, right? So, and then these two heights are given, the initial velocity is given, put all the numbers in, what is the number you got? The number I got is 12 meters per second. So that's the value of the final velocity. What is the direction of the velocity? Well, in this case, obviously at 32 meters, it's still it's falling, right? It's already falling at that point, so that's that. Okay, so that's how we use conservation of energy to solve this problem. You may say, well, okay, I see that, but I can just solve this using kinematic equations, right? So why bother? Why do I need to learn a different law and then solve it in a different way when I already can solve it using kinematic equations, Newton's laws? Well, because you don't always have constant velocity motion, right? If the constant acceleration motion. If the acceleration is not a constant, applying Newton's laws and kinematic equations can be really hard, okay? But conservation of energy, you see that when I set up this left-hand side and right-hand side, did I worry about acceleration at all? No, I didn't, right? I just need the initial and final values on the left-hand side. And then I also need the work on the right-hand side from the outside on the system. And then if the force from the outside is very simple, the interactions between these objects in the system, inside the system, can be still very complicated. That's fine, okay? But if the force from the outside doing work on this object, on this system, is very simple, then I can still use this law to, in a very complicated process, when the acceleration is not a constant, I can still make predictions using conservation of energy instead of kinematic equations and Newton's laws. Now, I'm going to show you an example where the acceleration is not at zero. You have to use conservation of energy to make a prediction. So that's a question I want you to look at on slide 3. So this is a pendulum question. We know how to make a pendulum, right? If you just attach like an object to a string, and then you attach the other end of the string to, like, you know, a ceiling or something. You just let it, pull it to one side and let it go. Then it's a spring. So what we want to do is this. Say, if I know the length of the string, I also know the angle where I'm going to release the pendulum. I want to predict the speed of the pendulum at the lowest point. Okay, so that's what I want to do. So this is the pendulum, right? So if I release it at an angle theta, so it's going to swing back and forth for sure, right? So what I want to do is this. If I know the length, so I'm going to draw a general conclusion. If I know the length of the pendulum, and then I can release it at any angle I like, so I can even decide this angle theta. But say I know these two numbers. I want you to predict the velocity of the pendulum, the velocity of the object, the pendulum bob, at the lowest point of its motion. How would you predict that for me? I want a number, okay? So let's see if I can use Newton's laws and kinematic equations to make that prediction. So you're going to draw all the forces. How many forces are on this object? Well, gravity is always on it. I always draw gravity first if I draw a Fourier diagram of an object. The second force is going to be the tension from the string. And that's going to be away from the object, right, parallel to the tension. So if I want to use kinematics, I would find acceleration. I would also need to make sure the acceleration is constant. So let's take a look at these two forces. If I want to find acceleration, I would do net force divided by the mass. Gravity is down, so this guy is constant, okay? I'm not going to finish all the algebra. I just want to figure out if the acceleration is constant. The tension, well, that's a little bit tricky. First of all, the tension changes direction. So at every point, the tension is going to be in different direction. If a force is in different direction, it's a different force. So it's not a constant force, right? So for example, at this point, gravity is still down. Gravity is always constant, always down, always the same value, but the tension is going to be like this. So at least the direction of the tension changes in this process. So it's not a constant force motion. It's not a constant acceleration motion. Secondly, even if you want to find the magnitude of the tension, it's really hard to find, right? You don't have a fundamental theory to help you find the tension, this whole process, right? And then also the tension, the magnitude, you can't just assume is a constant. Because the tension totally, the magnitude totally depends on how tight this string is stretched. And then there's no way you can predict that. So then you shouldn't just assume the tension is constant, right? As I said, constant forces are actually very uncommon in real life. Only gravity is a constant, okay? So when you don't know if a force is a constant, you don't assume it's a constant. You don't do that. So this is really actually a very complicated process, even though this is a circular motion, but because this is definitely not a uniform circular motion. So everything is changing here. So it's very hard to make that prediction using Newton's laws and kinematic equations, because there's a lot of changing factors here. Let's see if I can use conservation of energy to make that prediction, if that's going to make this process easier. All right, so let's see. If I want to use conservation of energy, I will set it up this way. Very nice. The left-hand side is still going to be these 4 terms because I have one object in this system. It has kinetic energy, it has a gravitational potential energy, and there's no spring here, so I don't have elastic potential energy. So left-hand side is going to be the same. And then I'm just going to find the final velocity if I call this the final point, the initial point. So that looks promising. What about the right-hand side? The right-hand side, you're going to calculate the work done by all the forces from the outside. So how many forces are from the environment on it? It's outside the system. Gravity, as I said, if you use conservation of energy in that format, you already define gravitational potential energy. Gravity is already in our system. You never need to worry about gravity on the right-hand side. Okay, but don't get it wrong. I'm not saying gravity is not doing work in this case. Gravity is still doing work, right? You can still do force times displacement times cosine theta. But it's only because we don't consider gravity as a force from the outside on this system. We consider gravity inside my system. So it's not a work. It's not a work from the outside. So I don't calculate on the right-hand side. So tension is definitely from the outside. Tension is something I need to calculate on the right-hand side. Then you may say, oh, then you still need to deal with this tension. This tension is really a trouble. We just saw that. It's not a constant. It changes direction. But in this case, of course, this is a well-designed problem for this intro-level class. This tension is really tricky. But let's take a look at the work. If I want to find the work of the tension, I would do tension times displacement times cosine theta. So I should actually do an integral, okay? But if I break this whole process into little pieces, let's see. Even if I want to do integral, at any point what I'm going to do is that I'm going to do tension times the displacement, very small displacement, and then do the same process at every point and add them together. That's the idea of integral, right? Even though at the end I may have an infinite number of small elements, but that's how actually I'm going to calculate the work done by the tension. But if I focus at this point, this is going to be the direction of the tension. This is going to be the direction of the displacement. Displacement is going to be tangent to the circle, right? Because this is a circular motion. Displacement is going to tangent. And this tension is just toward the center. Okay, because this is the center of the circular motion. Okay, if the tension is toward the center, so that's the radius, and that's going to be a 90-degree angle, because this is going to be perpendicular to the radius is going to be perpendicular to the tangent at this point, right? So if I want to calculate the work done by this tension and this very, very small displacement, That's going to be 0 to me because this is 90 degrees. And then on the way to the lowest point all the way through, you can find that at every point you draw the displacement, you always get a 90 degree because this is a very, very special, well-designed problem for this class, right? So at every point, the tension is always perpendicular to the displacement. So that means even if I want to calculate the work, I will get a 0 because I always get cosine 90. If you get a cosine 90 at every point, the tension is not doing work. It's not doing work in this process. This is a very special case, of course. So that's nice. That means this equation is not going to change, right, for this problem. So I will still have these 4 terms on the left. I still have 0 for the right-hand side, right? So even though the tension is an external force, but it's not doing work to my system. So that's nice. So that means I don't need the math. So even this algebra is going to be the same. Even this algebra is going to be the same, right? So all I need is just find the numbers. So this is more promising than Newton's laws and kinematic equations. So all I need to do is just find this VI, final height, initial height, and then finish this algebra. So that's how I'm going to make the prediction using conservation of energy. Now let's see. VI is easy. That's going to just be 0, right? If you pull a pendulum to one side, let it go, that's going to be initial velocity 0. Then I need these 2 heights. When you calculate the height, when you want to find the height, you need a reference point, right? Usually we would just pick the ground as the reference point, right? Something is has a 10-meter height with the ground. In this case, but remember, height is relative, right? In this case, I don't even care where the ground is. I can pick any 0 reference as I like, okay? So what matters is only this, the difference, right? Because when you do that, you're going to just only need the difference between the initial and final height. Now, how do I find this initial and final height? Well, first of all, let me rewrite this guy here. So now I'm going to pick a reference point. So what we usually do is this, because I'm free to pick any point as the reference point. So why don't we just pick one of these 2 points as my reference point? So I can make one height 0, right? So that's just going to make my calculations easier, right? So I'm going to redraw that. So I know that this guy is going to start from this point. It's going to end up here. Okay. Well, I'm going to redraw that. Okay, so that's the initial height. That's the final height. So usually what we do is that to make our calculation easier, I'm just going to pick one of them as 0 height. Because what matters is only the difference. So what we do, because a lot of people, they're afraid of negative numbers. So we just pick the lower one as a 0 height. So the other height is going to be positive, right? So in this case, why don't we say this is my 0 height? This is how where I'm going to count the height. So I'm making my final height 0. So the initial height you see is higher than that, so it's going to be positive. Or if you want, you can make the initial height, you say this is my 0 reference. This is how where I set up my coordinate system. Then this guy is just going to be negative, right? Just make sure that you get the signs right, okay? If you pick a 0 reference, you will always get the right answer. Just use the right signs. Okay, so let's do this. I'm going to pick the final height as 0 because I don't like negative numbers. So I have another 0. So I have a 0, 0 here. So the only thing I need is actually the initial height. So that's what I want you to finish first. Once you have the initial height, then the rest is going to be easy. So let's take a look at the question on slide 4. I want you to use the L and theta, find expression for the initial height, so that I can plug it in and find the expression for the final velocity I want to predict at that point. So how do I use L and theta to find this initial height? So if this is the height, right? So I'm going to draw this line. So this is the height I'm looking for, right? Okay? This is the height. If I draw these two lines, because this is the level of this initial point. This is the level of the final point. If I call this 0, this vertical height is the initial height I'm trying to find. So it's a little bit hard to see how to find that, but if I draw this line for you, this is also the initial height. Okay, can you see that, how you can find this height? This is totally geometry. How do you find this little height? How do you find this distance? How do you find this distance? Using L and theta, and then there's a right triangle here. Okay, if you still don't see that, think about it, pause it, think about it. How do you use L and theta to find this height? If you still cannot see that, I'm going to tell you another hint. If I know this, like say x, if I know this x, can you find this h height? Of course, because what is the length of this guy? That's L. That's the same string. That's the same string. So if I can find this x, this side, this distance, this short distance is going to be this L minus whatever this x is. Can you find an expression for this x? There's a right triangle here, right? And you know an L, hypotenuse, you know a theta. Can you find x and plug in, find the initial height, right? So that's what I want you to finish in the first part, okay? So this is the geometry. Once you have, this is actually the hard part. Once you finish this, you can plug in the expression to this conservation of energy. Then we can finish that. All right. So what is your answer and this to this question? First of all, this x. If you make use of this right triangle, what is this x? This is just adjacent to this theta angle. So it must be L cosine theta. Right, and this right triangle. And if this is L minus cosine theta, and then this distance, it's going to be the total minus x. Okay, so that's going to be equal to L minus L cosine theta. And if you factor out L, what do you get? Okay, so that's going to be this answer. That's going to be how I write this initial height if I call the lowest point as 0. Now let's go ahead and plug all the symbols we have, right? Initial velocity is 0, final height is 0 because that's my 0 reference, and then the initial height is this, right? So this is just going to become 0 minus 0, so you're just going to get GHI 1/2, and then you take a square root. All right, so finish this algebra. What is the final expression of this velocity? So that's going to be our prediction. If you plug this in, what do you get? You just get 2GL 1 minus cosine theta. So this is our prediction, and this is a general conclusion. So if you have a pendulum, you measure the length of the string, and you measure the angle you release the string. You can actually decide where you want to release the pendulum, right? So you will. It's going to be very easy for you to measure these two guys, and once you have measured these two guys, you let it go. You can always use this expression to predict the speed at the lowest point, right? You see, all you need is actually the length of the string, and the theta angle, the release angle. So I pick a L, I pick a theta, I can always make a prediction using this expression. And I can do an experiment to test this prediction, okay? Because all I need to do is just set up a pendulum. Actually, it's very easy to set up. You just need a string and anything attached to the string. And then how do you measure? So I want to test this theory, so I need to measure the speed at this point. But we can do that using a photo gauge. So you just place a photo gate at this point, let it swing. Make sure the photo gate is at the lowest point. So let it swing through the photo gate and then compare the speed the photo gate measures with this prediction, and you can confirm if this prediction is right or wrong. And that's something we can do. We will set up this experiment and then test our conclusion. We will do that. Okay. All right. I'm gonna stop here for this video.